It will sweep the spectrum between 41 megahertz all the way to 108 megahertz. Every time that it strikes a frequency, it picks up something from the neighboring stations. It just stops there momentarily. As it stops, the digit behind the D2A converter will stop and load itself to memory. Location 1, location 2, location 3. It's those buttons 1, 2, 3, 4, 5 in your radio, which is the number of the stations you're automatically set. And that's it. It will stay there. Every time you want to go to the station, you press the button, you're at it. Because those buttons, they bring from the memory the code corresponding to exactly that analog voltage that produces that capacitance, that produces that resonant frequency where the desired station is. So that's the principle. That's the application of this diode. Now imagine how much application that is. This principle, tuning, works for televisions, every television, radios, cell phones, communication wireless, scanners, mainly, that list of scanners sweeping from end to the top. It's that one. So it is an important thing to know about this, its existence. So let me get there again, as if it threw me out. Okay, so that's the story about it. Now, the second type of the capacitance that I want to bring to your attention is exactly opposite of this one. When that voltage is positive. When voltage is positive, gentlemen, a heavy current goes through the diode. The more positive you make that, a greater charge will pile up in this region, in the neutral region, so-called, in addition to what is inside. But the inside capacitance will be so minimal compared to this one, the larger one. This produces a capacitance called CD, diffusion capacitance. It is for forward junctions only. We do have a current there, and we get a much bigger capacitance there. The profile is shown here, right there. It shoots up very rapidly. This is the applied voltage. The amount of the capacitance, the forward diffusion capacitance, depends directly on the ID. So here, CD is directly proportional to ID and also tau t, which is transition time, that the electron makes a transition from one side to the other side. It's a very brief time. Typical time of a transition is only in the nanoseconds, 10 to the minus 15 to 10 to the minus 5 nanosecond. And VT is the terminal voltage. And bear in mind, what was the relationship between ID of a diode and the voltage of a diode? Do you remember that exponential relationship? Exponent? ID is IS, exponent VD over VT, the exponential relationship. So, if you want to express this capacitance in terms of the VD, substitute, and then you will see CD becomes exponential function of the forward voltage. That's why this curve that you see over here, increasing, this curve is actually exponential, very rapid, meaning it will give you very large forward capacitance. But is it useful? Here. Is it useful? Here's the problem. When a diode is in reverse, its resistance is infinity, like no resistance. So other than that 100K, we have nothing else. But guess what? If you make this guy forward, and do you remember the dynamic resistance in a diode? You know that slope, how low it was? It was like 20 ohm, 30 ohm. This diode, in the forward, it will show you the RD. RD, this is the forward dynamic resistance, which is only 5 to 20 ohm, or something of that order. Well, here's the problem. If you make a resonance circuit, LC 10 or 20 ohm is a very low resistance that will not resonate for you. It's like that vase example I gave you. It's like loading, you know, a lot of energy absorbing material in the vase. When you hit it, it will not ring because water absorbs the vibration and energy. But in this case, in the other case, in the reverse, the diode does not consume, does not dissipate energy. Therefore, causes the LC to resonate, and that's what we want. Okay, so we learned something about diode that you always handled it. You had problem solving, forward region, reverse region, etc., right? But if you look at the charge property of that, which is a pretty complex mechanism there, in the charge mechanism, it's different. When it is in the reverse, you have a charge buildup in the depletion region, which apparts and gets close to each other by external reverse voltage. And that causes a control of the capacitance starting from a zero bias voltage. It means when zero voltage is there, you've got maximum capacitance going to a lesser capacitance. We utilize it here for radios. In the forward, nobody utilizes. Actually, it is a nuisance in the forward because it produces capacitance, but it absorbs so much energy, which is useless for this application. And there is no way around it. You've got forward diode, you've got dissipation. Okay, so that's a useful thing to learn. What you can take from here is the following. Every junction, P-N junction, wherever they border, they do have this junction capacitance. It is either in the reverse, that junction has a reverse potential on it, then it follows this equation, or that junction has forward voltage on it here, which follows this equation. It means that capacitance increases with current in the forward. In here, that capacitance gets smaller with the reverse voltage. There is no current whatsoever in this situation. I is 0 because it's reversed. Okay, now with that, it's going to help you with the transistor. That's why I'm basically talking about it. One, just a summary. This is kind of an excerpt from a book. Let me see what is here. Okay, yeah, all of that is here. Here. Okay. Now, what do we have? What is really of your concern? Because we are going to talk about effect of those capacitors, and be sure you will get an exam on this one, because that's a high frequency effect in the amplifiers. So you did the CE, CC, common base, you know, everything, you know, was normal. A model, analyzed, that's it. But now it's a different one. Here is the transistor. Transistor has 3 layers. It has a P layer, known as base, N, actually this is the N, this is N plus, which makes the collector. This is the p-type. Now why n plus? We suddenly changed because that's the way these things are designed. So they get you get a substrate like that, heavily n-type, n plus. It is n, but it is very rich in donor electrons. Then on the top of that, you deposit a layer and you make a p region out of it, p material. And then on the top of that, you, sorry, the first one is n. Hang on a second. It works in the reverse direction. Sorry, for the n type, they grow a p, okay, and then they deposit next a heavier n in here. P. This n is on the top of the p. Sorry, it's there. P, and then n plus is down there. Now that makes sense. So this is n, p layer, and then we have another n plus layer, heavier n. Simply, you bombard it with a more concentration of phosphorus, and it becomes n plus. Then one becomes the base, one becomes the collector, and one turns into emitter, creating those layers. The n here and there, the collector and emitter parts, they are not symmetrical. Concentrations are different. That is why, because of this asymmetry, that is why you cannot flip the transistor in any direction that you like. Has it ever occurred to you, if it is NPN, why don't I use the N of the E for collector and the other one for the emitter? See, it's a logical thing. Somebody is the thing. But the thing is, it's not NPN. It's N plus PN. Okay? So when you're turning around, you have a totally different transistor. It's an NPN transistor, but functionally, the parameters will be different. Beta will be different. Let me tell you what will be the beta. It's called beta R, reverse beta. Beta R's are 1 to 10. So it's so small. Gain of 1. You don't want gain of 1 transistor, or gain of 5 or 6. But if you put them backward, that's what you will get out of it. If you put it in the right direction, collector and emitter in the correct position, then you will get high beta. Okay, so having said that, let's see which one is the junction, forward junction. Okay, do you recall the 0.7 volt we had at the time of biasing? Positive 0.7. Okay, volt. This is the forward. So this junction has a depletion layer which is very narrow. It has positive charge on one side, negative charge on the other side, and it forms a capacitance between the base and the emitter. This sandwich layer between the P and the N, it's a forward junction because B is positive with respect to the E. 0.7 is a positive voltage. So you get a forward voltage. This capacitance is called C pi. C pi. Then there is another junction between collector and the base. Okay, let's check our transistors again. Base emitter, do you remember collector to emitter? VCE, quiescent voltage, collector to emitter. We took it 5 volt, 6 volt, 10 volt. It makes this junction into reverse. For example, if you have VCE of 5 volt, then VCB is 4.3 volt reversed. This junction will be reversed. If this is 5, that is 0.7, and this is 0. 5 is positive with respect to 0.7, isn't that right? So the top junction, which is another NP, will have a depletion layer which is much wider. Much wider. As a result of depletion layer being wider, there will be a capacitance between the C and the B, because on both sides of the layers we do have a capacitance. This capacitance is called C mu. That is the collector to base reverse bias junction capacitance. It has nothing to do with the current that goes through, but it has to do with the amount of the voltage that reverse biases. Okay, so what do we get now? Go back to the transistor model. I'll show you in here. Okay, let's review our transistor model, R-Pi and the GM. Do you recall that, R-Pi GM? We didn't have this business before. These two caps were absent. But now, more complete model of the transistor for the topic I'm going to talk is going to be R-Pi. There is an internal capacitance C-Pi going parallel with it. There is another capacitor called C mu, which is collector towards the base. What's the cause of that? The electron hole recombination here, one junction, electron hole combination in here, which is a forward junction. The top one, C mu at the top, because it is reversed, look what it follows, formula that it follows. C mu 0, that's the collector to base, 0 voltage bias junction capacitance, C mu 0, and that's when VCE is equal to VBE, so the two are level. Then you over radical 1 plus voltage VCB, collector to base voltage. So here we can say what is our VCB. 0.7, that's 5. So our reverse voltage between C and the B is 4.3 volt. You make this to a higher bias, say 8 volt, then you're increasing CB, you are decreasing CB. It's better, actually. You've got less capacitance inside at a higher voltage bias. Manufacturer will give you all that information for every transistor intended to be used in high frequencies. So, but just check the relationship, how they go. It's inverse radical. So low bias, high bias. And you get a higher VCE, you get a smaller kind of feedback capacitance. This is known as feedback capacitance. Guess why? C is the output, B is the input. The bridge between out and in is that C mu, which is cause of the trouble.